And of course, on the top of that, we have famous three curses of dimensionality. So each time we try to decide what to do, we have a state variable. State variable in economics most often it's capital grid. It's most basic, and no model can. Well, some of the models, but most of the models have capital grid. And let's imagine. Well, most of people have just one dimension, so it's kind of they are limiting their models by one dimension. But if you have more than one dimension, you immediately get L power k state of the nature at a given at each particular moment. And then, of course, with this capital, you do something with the capital, you produce something, you get the outcome. And again, this outcome is subject to some random shock. Maybe there's some lottery because you negotiated with your capital provider how you share your output. So there is an outcome, and again, this has many dimensions, it has many possible grid values. You have to have certain grid values, otherwise your problem is kind of not very interesting. You have to have many choices, many potential outcomes. So there's a second source, and then of course the decision that you make is also a vector possible decision, which also has many options. So this is it, sort of dimensionality problem. And this is a simple example that you have just like a simple investment problem that you have 30 different businesses, in each you have certain potential share of the ownership. You have 1/2, 3/2, and so on. If potentially you consider just 10 values, you have 10 returns, and so on. So what I want to stress here is that economics problems get really complicated really quickly if you try to solve them directly without any sophisticated method. If you say that your problem is so complex and so hard to solve, it doesn't mean that your problem is actually good. It means that maybe you're doing something not very smart in your problem. And just imagine that if you have such a high dimensionality, some people swear by parallel computing, grid computing. And imagine that you can speed up your execution by using 10,000 grid points, 10,000 computers by 10,000 times. That's 10 power of 5. If you have 10,000, 30, that doesn't help you a lot. I mean, it's still a lot more than computational power that computational power can afford. Now, again, I want to stress this point that your problem has to be specifically good for a particular way of computing. That there is no free lunch theorem in computing as well as in economics. You cannot get much mileage out of any computational method unless your problem is specifically formulated to take advantage of it. For example, this parallel computing is very good, but it's very good for a very particular set of problems. Like take example of New York Stock Exchange. There are 8,000 stocks trading. There's probably somewhat like 2 gigabytes of tick data. So if you want to analyze that, if you want to analyze what happened during the daytime on one particular stock, yeah, it's very nice to have a grid which will process in parallel all those information, so you don't have to sequentially process it. That could speed up tremendously. But on the other hand, why do you need it? I mean, your model has to require this, and maybe you just need one data, you just might need one price for the whole day, so you have to justify the usage of such huge volume of data, such huge volume of computational power. So I want to say this again because some people have the idea that if you put just raw power into the computation, it will help. Usually, you have such hugely complex problems, such huge dimensionality, potentially such huge dimensionality. Throwing raw power doesn't really help you. It slices very finely. So you have to reformulate the problem first in order to take advantage of specific computational method. And one of the way of doing this is actually, I'll give you a simple example of how you reformulate the problem. It's a simple T-type problem that has 20,000 possible states. Are you going to do sequential search of all 20,000 possible states? No, you don't do it. You know the solution already. It's empirically known that how you can win in this game, right? You don't need modeling. Well, of course, if you increase dimensionality, that's kind of getting trickier, but that gives you a good idea of how you can immensely speed up your solution for some cases. And here, again, in another example from Intercontinental Airlines. First when they try to model the scheduling of their airplanes to minimize the cost, maximize the profit, they try to do it like simple, straightforward ways, so to write all the equations and use very advanced simplex solver. It's the most advanced solver that's existing. So it took them days to solve this problem. But they have to schedule it, at least in our basis. If something happens, bad weather hits Boston, they have to reschedule the whole flights immediately. They cannot wait days to reschedule that. So they kind of come up with good empirical ways to reduce the dimensionality of those equations and solve the solution in 2 seconds. That's without looking supercomputer without looking. It's just being smart about how to solve it. And then again, that's kind of getting rid of the kinks. If you know, there was a nice line of research in contract theory about how to structure debt contracts, and there was a very famous result by Professor Townsend, which says that the standard debt contract is the optimal one. So basically, you allow, if you give money to an entrepreneur, you don't monitor him what he's doing, but when he fails, then you take over all his assets and you completely take over what he's doing in case of bankruptcy. And then sometime later, there were few papers which says that no, the standard debt contract is not optimal. The optimal contract is the one that you randomly monitor the progress of the entrepreneur. And that's, of course, the government would like that, right? I mean, you want to have as much monitoring as possible. So it seems that economic theory proved the point that government should monitor the entrepreneur, and standard debt contract might not be optimal. But then those guys actually tried to put a number on that, and they found out that the welfare loss from suboptimally imposing non-stop plastic monitoring is just this one. I mean, that's 0.003 of 1 percentage point. So if you switch to more optimal, it seems like analytically it's clear. Standard debt contract is not optimal. You should switch to random monitoring. I mean, that's if you just leave it at analytical stage, that's very clear solution. There's no doubt in it. But if you put a number, you see that this game is so small that just imposing this monitoring cost will completely get rid of this. So even some numbers can completely change what you think is actually happening. And here is one of the first models. I have to move quickly. So this is 1,000-year model of costly insurance of entrepreneurial risk based on Greenwald-Jovanovic model that we are trying to put into some policy, kind of make policy that is in use. So this is the standard AK model of economic growth, but it has divide this population into 3 subgroups: the people who are not capital constrained and who can start a new business, the people who would never start a business because startup cost is so high, and the people who can make transition. So this is, again, we concentrate on people who make this transition. That's where the most interesting thing happening. So financial intermediaries provide a major service. They provide insurance against idiosyncratic shocks, so they can basically see the better, because they have so many entrepreneurial projects, they kind of see how big the return, the possible return can be, so they kind of know the optimal return. And if you just do your business on your own, you're subject to all idiosyncratic shocks that those financial intermediaries in this model are supposed to be insured.